Well, let's look at the second statement. That's the typical statement. Here's the arbitrary second order linear equation in standard form with the arbitrary initial condition and want to show has one and only one solution. We've seen that many times before. We're going to focus on uniqueness part first, and then we're going to reverse the argument to show this exactness. So the key idea relies on the decomposition. We're looking at the second order linear operator, and these two things is decomposed into one first order followed by another one. So we can kind of solve this equation one at a time because we know how to solve the first order equation. So we start with a fictitious solution y, whether it exists or not. If it exists, we go through these established implications rigorously so that you end up at the statement that if there is a solution, it has to be this particular and specific one. So that proves the uniqueness. So I'm rewriting here in terms of operator. So this is the second order differential equation, and this is the operator acting on y is equal to phi, and we can replace it with that factored form. So here is decomposed. We first do this first order operator to y, followed by this first order operator into this function, and we want to this is supposed to be equal to this phi. So idea is, because this is the second one, it's then acted to this function, and we actually solve this one first. We have to go through that order. So we're going to replace this function to be just one function. There is a function, we can call that entire function to something like z. So that if you apply that operator to y, then it's y prime q times y. So that's a function, and we're going to call that function z, function of x, zx. So when we replace that, this becomes just a z, and this is just a first order linear equation in z. So we can solve it, and we know it's unique, but we're going to write that down so that's clearer altogether to establish uniqueness and exactness. So in the typical differential equation form, if you apply that operator to z, is z prime plus pz equals phi. The way we solve this first order linear equation is multiplying the integrating factor, which is e raised to the antiderivative of this coefficient of the linear part here, first order power part. So after we apply the integrating factor here, what we're going to do is we're going to integrate. In this proving uniqueness and exactness, it's better be just a definite integral, so everything is concrete and clear. So when you do the definite integral, we need this initial condition. So let's think about initial condition for z of a. Z is defined like this, and we want to know first order, just the value, function value there. What is za? Simply you plug it in here. So if you plug in x equals a there, we have y prime and y of a. Q is a function that it's computed when you decompose the operator. So QA is there. Whatever this number is, we're going to call it C. That's a constant. All that matter at this point is as computable. It's kind of part of the given information, where we used both YA and Y prime of A. Okay? So here I'm multiplying integrating factor. This is capital P, and this is lowercase p. So if you multiply integrating factor e to the p, then this is supposed to be the derivative of e to the p times z. And I also multiply that integrating factor to the right-hand side. Now here, if you hit the integral, then knowing that this is the derivative of this part in here, and we're going through definite integral, this whole thing is a derivative of this part. If you differentiate this one, you get z prime. If you differentiate the first factor, you get exactly that. So that's the antiderivative. And we're doing definite integral, so you have this function part minus this function evaluated that definite integral at a. So we plug a into this form. So it's e to the pa, and z of a is abbreviated to be c. And we just put this definite integral on the right hand side, Phi is just an arbitrary, nothing particularly specific, but it's known function. So this is where we are. Let's solve for z. So we add both sides this thing and this part, which is a constant that appeared in here, this part, and multiply e to the negative p to isolate z. So e to negative p is multiplied to this part, and this whole thing was already there in the right hand side, and multiplying e to the negative p. So z is this specific function. Phi is given, p is the antiderivative of the one of the coefficient of the decomposition. Antiderivative, everything is all unknown and specific. So this question is about the function y, and think about how this z and y are related. Okay, here's how z and y are related. This y prime qy was this zx. Now zx is this particular function now, and this becomes a first order linear equation set to some function in x. Okay, I forgot where I was. I hope I'm in the right place. Since we're doing this integrating factor again, so q is the coefficient of this y part of this linear first order linear equation. So integrating factor is e to the q multiplied everywhere, and that becomes the derivative of eq times y, right? So the same part. So when we integrate both sides, definite integral at a, we pick up this main function part and subtract it by this value at a, and we're putting this definite integral to the right hand side with the dt in there. Now if you isolate this y part, you get this function right there, and just make sure that this is nothing, no part here is unknown. Z is something that we found, and every part in that z is known, integral, and a is initial value, and q are antiderivative of the coefficient in that decomposition part. So this is the function that y has to be if that x exists, right? So that proves the uniqueness. So this proves the uniqueness. So existence, we're going to define this function as an independent statement, and we're going to go through the reversibility of this statement carefully. All right, for the existence, we have to clear that about what is that the function that y we started with. Y is this function, e to the negative q. Q is the antiderivative of the decomposition, and c1 is the part of the initial condition, and z has to be defined. So next part will be the definition of z. So q is this antiderivative, and z must be this function here. So let's see, e to the negative p plus pa. C, everything is determined. C is not given, in that if you think about the original problem, we have C1 and C2, but Z looks like this. Phi is part, and P is the antiderivative of the coefficient. So we have to specify the C, and that C is a C2 plus QA C1. Everything is known here. So that's the setup. Then we're not going to just say here, the implications are reversible. We're going to go through carefully and figure out which part's non-trivial. So it's the same slide. I'm going just backward, that we started with this function, and let's see the next argument. So what could be the process that describe this one to that is just subtracting and adding both sides. It's obvious. You just move things around and multiply. That's possible. What could be the operator describe going from here to there? I'm here to that statement is differentiating. You differentiate this function. That's a constant part that becomes 0. If you apply the product rule, you get exactly this one. And fundamental theorem calculus, take this integral part to this function. So that's simply the derivative. And going here to there is canceling e to the q, which is non-zero all the time. That's a key part. Non-zero, therefore you can cancel it. So from this part to that part is it's a bit strange, but what it's really saying here is writing down what the z was, and z was defined earlier here. So this is kind of a one statement. It is not necessarily followed from here. We're just writing down what z was. And also the next statement is, if the z is like this, we can just reorganize it like this, multiplying, move things around and multiply e to the p, things like this. So this is the statement we have. This is how y and z are related, definitely. And specifying the z in this form, then we have this type of statement. I think I was a bit incorrect in how to interpret this statement to go there is that we have just established this y prime plus qy equals zx, and this is true when z is that function that we started with. Sorry about flip-flopping. That the first thing I was saying before I think was correct. This is, we just stop here. This is how y and z are related, and from here it's kind of separate statement. Z was defined like this before, and we kind of reduced this thing to some statement about the z. So I'm going to box this part here. We're going to come back, but from here is the statement about z itself, not relating y. Alright, so I boxed it. So this is how y and z are related, and we'll come back to this one. So here's this definition of z the way we started with, and this is just adding and multiplying. You get it here. And from here, how to get to the next part is, of course, reversing this definite integral is a derivative. So if you differentiate this one, this is a constant, so we only had a product rule applied here, and that's what you get, and fundamental theorem of calculus, and simplified right-hand side to this part. Now, if you cancel the common factor of e to the p everywhere, then note that the z of a is this initial value. Then you get to here after you factor it. Then z prime plus pz is phi. So that can be written in terms of operator algebra like this. So from here to there is some statement that's fell out of the independent statement, what the z is. There's no y involved in here. Alright, sorry, shook a little bit. Y involved in here. So this is where we got this statement. This is where we replace this statement here. Z is replaced by this equality in there. Then we're going to have a statement about y that we started with. So since this z is y prime qy, it's written down here. If you replace that with this y prime qy, it can be easily written as an operational term like this. Then after this, of course, and these two things expands to this one, that's the part of the theorem. Right, keep making this mistake, but still there. So if you start from there, y defined like this, and z is a part of the definition of y, and it has its own definition like this, then we can show y satisfy this differential equation. Now it remains to show that y then, if you go back to the definition, it satisfies the initial conditions. So you probably need this, the value of za and everything. But let's go back, see if we can easily verify the initial condition. So here's our definition of y, and see if you get c1 when you plug in x equals a in there. X equals a, that goes there, make this entire second term 0. X equals a, put it in there, that becomes e to the 0, it's 1, so it picks up c1. It's nice. But the derivative version is not here, so let's go to this statement right there. We do have this statement along the argument. za is being c here. Maybe I think we should look at this statement first. The z here, z is that was sure that's the definition. If you plug in x equals a in there, that part's picking up c, and that part is 0 as x equals a. So we have the statement like this, and the z of a is c, and we defined that and c to be c2 plus qa c1. That's part of our definition. Now we do have that identity zx equals y prime plus q times y. So if you plug in x equals a in there, then we know y of a is c1, so that part matches. So everything canceled, it forces y prime of a to be c2. Okay, so the first, you look at this z identity, quickly pick up that za is a c, and we already checked that ya there is a c1. So with the c1, replace it in there. So that's a part of the definition of c. That makes y prime of a c2. So we're just looking at the one-way direction argument and try to make a correct logic out of it when we reverse it. So I think that proves the initial conditions as well. So therefore, the statements were all reversible and it satisfied the initial condition, so this proves existence.